Hello, my name is Terry Soul, and this is Programming Chaos, a channel devoted to programming projects to help you improve your programming skills. Today's topic is Lindenmayer-systems, also known as L-systems. They are used to generate all sorts of interesting graphical structures. And the basic idea, sort of simple L-systems, is that they're using rewrite rules to draw complicated, usually fractal images like the ones that we see here. So to begin with, to understand how L-systems work, we have to understand a little bit about grammars, because the way that we define an L-system is by defining a grammar. That is, the rules that make these images or make these systems. So as you may have been able to tell from the intro, the basic idea is rewrite rules. So we start, for example, here with a line, and then we replace that line with this top hat shape. And then for each line in the top hat, for example, this red line here, we replace it with its own top hat shape. And the same thing, this green line becomes a little top hat. And so we keep doing those rewrite rules, and we get more and more complicated shapes. What we need is a formal way to define those rewrite rules, and that's where this notion of a grammar comes in. And it's the same as you have grammar for a language. It is the rules that define what is a valid sentence in a language or what is a valid image. So every grammar starts with a start symbol. I'll just use S for the start symbol. And then there are variables associated with the grammar. So the start symbol is always a variable, and we can have other ones usually represented as capital letters. And the idea, as we'll see, is those variables are the parts that get rewritten. And then if we have variables, we also have constants, or what are often known as terminals, usually written as lowercase letters, and those are not replaced. So in this case, you can see our line gets replaced with a top hat. Well, terminals or constants are not replaced. They just become part of the final figure. In this case, I'm using an L and an R because we're going to think of them as taking a left turn or a right turn. Part of how we'll define a shape like this top hat is as left and right operations, and also as forward operations, but the forward operations will replace. And so that's the fourth part of a grammar, is the replacement rules. And so it might be something like, well, if you have a start symbol, replace it with a forward symbol and a turn right symbol. If you have a forward symbol, replace it with another forward and a right and another forward. And by using those rules, we can build longer and longer strings. So this is what happens if we take our replacement rules starting with a start and just keep writing them. We get longer and longer strings. And you can see, for example, the start becomes an FR. This F is replaced according to the rules with FRF. So our FRF. And then this F gets replaced, and this F gets replaced, and the R in the middle just stays unchanged because that's a constant. And then we can take those strings and translate them into an image. Now, it's worth pointing out, these rules are not quite the ones that will generate this image. I need a more complicated rule down here to get those images. So this is the basics of what a grammar is, and we can use it to generate images by sort of creating the instructions to create a particular shape. Grammars are hugely important throughout computer science. In particular, every programming language has a grammar behind it that defines what is a valid program. When you get a syntax error, a missing semicolon, or an unmatched curly bracket, that is the compiler telling you you violated the rules of the grammar by leaving out a semicolon or by forgetting a matching bracket. The topic of grammars is a huge one. There are whole courses devoted just to grammars. We're just going to barely touch on them so that we can apply them to our L systems and make these cool images. So with that in mind, we can start the programming, and the two big pieces are going to be this notion of using our rules to expand a string and then translating that string into an image. Okay, let's get started. The place we need to start in the code is with our expand function. It's a function that we give it a string and it applies our rules of our grammar to generate a new expanded string. And before I do that, the very beginning is our start symbol. So I'll just use S as our start symbol, and then we're going to pass that string into our expand function. So the expand function takes a string, expands it, and returns a new string. We'll begin by creating that new string, which initially is empty. And then we need to go through every character in our initial string, expand it, and as we expand it, we'll add the expanded string onto our new string. And the general idea is for every character in S, we've got to apply our rules. So I'll use a for loop to go over each character in S and apply the correct rule from the grammar. So the way that I'm going to do it, as I said, a for loop to go over each character. We use the character at to find the correct character in our string. And then I'm going to use a switch statement. So for each character, we'll have a particular rule that we apply, beginning with our start symbol. So we need a rule that applies to the start symbol. So there we go. That's our rule for the start symbol. If we see an S, we're just going to replace it with an F, and then we need to break. That new character gets added onto our new string, and now we need a rule for how to handle an F. So that's our next case. So there's our rule for if we see an F, we're going to replace it with this longer string of characters. And notice that F is acting like a variable because it has a rule to replace it. And then L and R are going to be constants. And so we're not going to replace those. And so the way we do that is we just put in a default rule that says for the other characters, keep them the same. So there we go. If we see, for example, an L, and L's will be put into the string by this rule, that's going to be one of the default cases, and we'll simply take the character that we're looking at, that is the character at location I, and copy it onto the new string. So an L will be kept around unchanged. If we want to think about this in terms of the grammar, we can put the rules in of our grammar sort of as comments. So we have a rule that says if you see an S, replace it with an F. If you see an F, replace it with this much longer string of characters. So formally speaking, those are the rules of our grammar, just represented in code. So now I can clean up the rest of this function, finish off the for loop, and return our new string. To check that this works, what I want to do is start with our start string, expand it, print it, expand it, print it, and make sure that everything is working right. And I'll just do that inside the draw loop. I don't want to do this continuously. I don't want to do it forever because our strings will just get much, much too long. So for now, I'm going to limit it to just the first 3 frames. So we'll only update our string, the first 5 frames. So we'll only update our string 5 times. And we can see how that works. So there we go. We get a window which doesn't draw anything yet. But if we scroll up, our initial string is an S. It, following our rules, gets replaced by an F. That F gets replaced by this sequence. And then every F in this sequence gets replaced by that sequence itself. So this first F becomes a whole set of characters. And then there's an L, so the L is kept unchanged. And then the second F here becomes a whole string of characters. Actually, this string of characters. So that's how our rewrite rules work. They take the string and they just keep expanding it and expanding it. So now that we have that part working, what we want to do is get to the fun part, which is turning this into an image. And so the idea is actually quite similar to what we have in our expand, except instead of applying rules, we're going to apply drawing commands. So our F is going to represent a forward, our L is going to represent a left, our R is going to represent a right. And if you're wondering, well, where did this rule come from? Well, that turns out to be the one that matches the sort of top hat I had before. It goes forward, forward, turns left, goes forward, turns right, goes forward, turns right, goes forward, turns left, and goes forward. So that will draw us the little top hat that we want. So let's set that up in our drawing window. And in order to do this nicely, I'm going to use a push matrix and a pop matrix to reorient our coordinate system to sort of a nicer location on the screen. I'm going to move down to nearly the bottom of the screen. So I'm moving my coordinate system down to the height -20. And then we need this same sort of for loop, and in fact this same switch, except for each character in the string, instead of applying an update rule, we'll apply a drawing command. The first case we worry about is the forward case, and there we just draw a line forward, and then we'll translate to the end of it so that we can do the rest of the drawing. There we go. So if we see an F, we draw a line with a length that I still need to define, and then we translate to the end of that line so that we can be ready for the next piece of the drawing. That's for if we see an F in our string. If we see an L, what we want to do is turn left. And as with the length of the line, I'm going to set the angle as a variable, and then we'll define what that angle is depending on what kind of an image we want to draw. So there we go. If we see an L, we'll rotate left. If we see an R, we'll rotate right. And if we see an F, we move forward. If we see any other symbol, for example, if an S, we should replace all of our S's, but if an S or some other symbol shows up, we'll just ignore it. And so now all I have to do is go in and define my length and my angles. Okay, so there are the variables. For angle, I want to do right angles right at the moment. So a right angle is just half pi. So for the length, I'm going to start with quite a short length, and we'll see, it'll make it a little hard to see at first, but then our image will grow as we apply the rewrite rules. So I'll just start with a length of 5. And in order to see this sort of step through slowly, I'm going to slow down the frame rate. So that will give us 2 frames per second. And I can expand this so we can do more than just 5 iterations. I think 9 iterations should work. And you'll notice I have a small error here. The string that I want to expand in draw is str. That is my global string that I'm working with. So here we go. So there's our line, our hat, our repeating hat shapes keep getting embedded, and each time we get this more and more complicated fractal shape. You can start to see repeating patterns, right? This sort of almost cross-like shape that gets repeated throughout. This is known as a Koch curve. It's one of the classic L systems. And I see that I have an error message here. I can't use push more than 32 times. Hopefully you already caught that error. I had missed it. I have my push matrix, but I forgot to put at the end to pop that matrix back off. There we go. That should fix the error, so we can run this again. A slightly nicer way to do this is to start with a long line, and then as we do each iteration, instead of the whole system getting bigger, the line length gets shorter, and so we keep sort of the same overall size. And I'll show you what I mean by that. Instead of starting with a short length, I'm going to start with a much longer length. In fact, 3 times the width. And then on every iteration, when we expand the string, we're also going to shorten our length. So it's 1/3 as long. And the reason why it's 1/3 as long is if you think of our little top hat, we've got 3 sections in it. For one line that we started with, we divided into 3 sections. So each section should be 1/3 as long. So now we start with a long line, but every time we go through, we make a shorter version of it. And in this case, because I didn't replace the background, we're getting all of the old versions. So we can see the original line, and then we can see the first iteration top hat and the second iteration top hat, and so forth. And so this is not a bad pattern at all. If you want, we can go in and add the background in. So now it'll erase each iteration as we do it. And so we start with a line and then a top hat, and then it gets more and more complicated as we go. So as I said, this is a Koch curve, one of the classic L systems. And now that we have the basic code in place, it's simply a matter of changing our rewrite rules to get lots of other figures. So let me go in and change the rules so we can get some other famous L system forms. So here's another fairly famous L system. And to create it, I'm just going to rewrite our grammar rules. So first, the start will go to FLGLG. So this is no longer accurate. And I need now a rewrite rule for F. So there's the rewrite rule for F. And because I have this new variable, so in this case I have two variables, I need a rule for how to handle G's. And a G simply becomes a GG, and as before, any other character I'll just keep the same, in particular my lefts and rights. I'm using L and R. If you look on the web, these are often represented as a minus for a left turn and a plus for a right turn. I like L's and R's instead. So now we have to change our drawing rules. Both an F and a G, we draw a forward line, so that remains the same. Our angle, we need to change. It should be 120 degrees, which is 2/3 of a pi. And for the length, I'm going to start with a length of 2, and I'm going to reduce it by 50% each time. There we go. So this gives us an image known as the Serpinsky Triangle, another fairly famous L system. And from these two examples, you can see that just by changing our rewrite rules, we can produce all sorts of interesting, complicated fractal shapes. And a quick search on the web under L systems will give you all sorts of other rules that you can apply to generate all sorts of shapes that you might like. And of course, you can go out and try and create some on your own, keeping in mind this idea of rewriting the same pattern over and over again, sketching them out even a little bit like I did with the top hat at the beginning, can make it fairly easy to come up with your own interesting shapes. What I'd like to do next, though, is apply some color so that we get some of the images we saw near the beginning. And a simple way to do that that gives some really nice effects is to update the color every time we draw a new line. So I'm going to define a hue, and then each time we draw one line in our image, we'll change the hue a little bit, and that'll give us some beautiful rainbow effects. It also helps to make the background black so that they stand out a little more. So let's go ahead and do that. I'll begin by defining a hue variable. And I'll need to change the color mode to HSB. When I use the HSB color mode, I use 360 for the hue to get a full color wheel, and then 100 for the saturation and brightness. So I think of those as being between 0 and 100%. Now, each time we draw a line, I want to fill it in with that hue. And for now, I'll use the maximum saturation and brightness. When we finish drawing a line, I'm going to update the hue slightly. This is a number that you can play with, but basically because there are so many lines in these fractal patterns, I only want to update the hue by a little bit each time. And then because I'm going around the color wheel, I'll put in a mod 360 at the end. Here we go. So there you can see sort of the rainbow color effect. And to get this a little stronger, we might want to increase the frame rate and, as I said, make the background black. So let's comment out the frame rate. There we go, a nice rainbow effect Serpinsky triangle. We can do the same sort of thing, but instead of varying the hue, we could, for example, vary the saturation or the brightness. And it turns out changing the brightness has a pretty cool effect as well. So let me show you that. I'm going to set the hue to 0, which is red, and not great programming practice. But I'll use for now as a demo the hue variable, but I'm changing here the brightness. And so this gives us an all red triangle, but notice regions of it, the brightness change, and a lot of it is still fairly bright because my brightness goes to 100, but down here I left my rollover at 360. So if I put in a 100 there, now more of it is dark, and it's sort of a little bit of an illusion, but it looks like the darkness is sweeping through in the other direction. So there's a few things we can do to play with the colors. In addition, we don't have to draw just one L system at a time. I could draw multiple ones on the screen, overlapping or mirrored in different ways. And so, for example, one of the images at the very beginning was the Koch curve, but drawn in the upper half and then mirrored in the lower half. And if you go back and look at that again, you'll start to recognize it. So now that we have the basic L systems, we can start to combine them, color them in different ways, and otherwise get all sorts of cool effects. If you create a particularly exciting, interesting looking L system, please feel free to include a link to it in the comments below. Or if you have a favorite L system, one that you particularly like, again, please mention it in the comments below so we can share them. There is another class of L systems that's particularly interesting, and those are ones used to draw branching structures, so things that look like bushes or trees. And the key there is the rules include ways to back up and branch off in another direction. And that involves going in and using some transformations. Takes a little time to set up, so I will save it for a future video. But if you want, you can go explore those on your own as well. Thank you.